Good morning, everyone. Welcome to our second keynote for the week on outflows. I chose for the image today an observational image of Centaurus A, known for its relativistic jets that are being flung out by AGN feedback. Perhaps we'll hear something about that in our keynote. This is just our schedule of 8 themed weeks. So we're finishing up outflows this week, and next week we'll move on to inflows. Just a reminder that we have a YouTube page which features new results videos that are contributed by members of the community. These are 4-minute long videos. There's a video on the thing for making a video. We've been a little bit light this week, so maybe people are out of new results. I hope that's not true, but we encourage people to submit videos, and we'll post them on the channel. We've got like 80 subscribers now. Everyone's watching these things, so it is getting a pretty good coverage by the community, and hopefully your results will be seen by others. On that same YouTube page, we're featuring junior scientists. So if you're a junior scientist who's potentially on the job market, you can go to the Halo 21 on the market Slack channel and submit a video about yourself. We just had a submission from Ranita Jana from the Raman Institute in India. So check that out. And we're also encouraging people to post job listings. If you're hiring, feel free to post in that same Slack channel. I know we've had a couple of jobs posted. So definitely a place you want to check out, especially if you're a junior scientist potentially looking for a job now or in the next couple of years. So today we will have a keynote presentation by Tim Heckman from Johns Hopkins that'll take us through the hour. And then we'll have a short break of about 5 minutes or so, and then follow it up with a panel discussion featuring Dr. Cassie Lackas from Space Telescope, Professor Crystal Martin from UC Santa Barbara, Professor Evan Schneider from University of Pittsburgh, and Professor Chuck Steidel from Caltech. During Tim's presentation and during the discussion panel, we encourage, rather than typing things into the Zoom channel for questions or comments, we encourage people to do so in the Slack channel, Halo 21 Week 5 Outflows. That will allow it to be more preserved after the Zoom channel just closes, and allow other people to comment and in a threaded way, so it's a bit more organized, and you can get some pretty organic discussion taking place there. So, and what's more, during the panel discussion, which I'll be moderating, I'll be selecting questions and comments from the Slack channel to ask of our panelists, and so forth. Another thing that you can do is by clicking on the little emojis next to a comment that you like or perhaps dislike. That's effectively a way of upvoting it, so that if I see there's a comment that has 12 upvotes on it, I'm more inclined to ask that of our panelists. So that's one way you can kind of informally vote in the Slack. Okay, so our keynote today is given by Professor Tim Heckman. He needs little introduction. He's one of the most senior members of our community, and as a chair at Johns Hopkins, as well as a member of the Academy, the National Academy of Sciences and the American Academy of Arts and Sciences. Tim has done, he's an observer by trade. He's worked in a variety of different wavelength bands, including optical, UV, radio, with surveys like MANGA, Sloan, FUSE, Galaxies. Much of his work is extremely seminal and has defined the direction of our field in terms of winds and outflows and AGN and starburst driven winds. And so I'm really excited to hear what he has to say today on the topic of outflows for us. So thank you for joining us, Tim.
Thank you. This is great. Thanks
Perfect.
for inviting me. I've been really enjoying the workshop so far. And I wanted to spend some time walking you through galactic winds and how they might impact the circumgalactic medium. So as I tried to put this talk together, I realized I can't cover everything. So I decided to have some points of emphasis. I will talk about a whole range of redshifts, but the bulk of the talk will be focusing more on the low redshift universe. And this is because, as I'll show you, these outflows are multi-phase, and most of these phases can only be looked at in the local universe. And also, it turns out that you learn a lot of interesting things by spatially resolving the flows, which is also a lot easier to do than the nearby universe. I'm going to focus on feedback from stars and not talk about AGN feedback in massive galaxies. I think this was really, while incredibly important, it's a sort of a separate talk. And I would invite everyone to join Mark Voigt's after party, where we're going to talk about this at great length, I suspect. And I'm also going to, even though the outflows are multi-phase, I'm going to emphasize primarily the warm, that is 10 to the 4 K up to, say, 10 to the 7 K gas. And this is basically just being practical. This is where most of the data pertain to. And I think they're the phases of the outflow that probably have the most relevance to the circumgalactic medium. So this is just an outline. I wanted to just start by giving you a brief motivation and some background. I wanted to walk you through M82, which is the best studied galactic wind. You can see all the different phases and the intricacy of these outflows. And then talk about how M82, in fact, is not unique. It's typical. And I want to emphasize sort of spatially resolved observations of the hot and warm phases of winds in the local universe. Then talk a bit about how we measure systematic properties of winds, things like outflow velocities, mass flow rates, and so on, and the scaling relations that result, and then conclude by summarizing the observational evidence that winds impact the circumgalactic medium. So motivation in the biggest picture, of course, is we all believe that feedback regulates the efficiency of turning accreted gas into stars. And I think one really interesting way of looking at this is to consider, this was from a paper last year from Beruzzi et al., which basically says that the global efficiency of converting accreted baryons into stars has been roughly constant with redshift, and it's of order 10%. So the data are just the normal Maddow plot showing the star formation history of the universe, and then the red and blue lines are basically a model in which effectively there's just a constant efficiency of conversion of accreted baryons into stars as a function of time. So that's actually pretty simple, right? The Maddow plot is often called mysterious and you need feedback and so on. It really is primarily just tracing the accretion history of dark matter and baryons into halos. So why is this interesting? Well, one of the clues as to what's going on here, why is it 10%? Where does the 10% number come from? Is that there's almost no evolution in the omega H1. So if you look at the plot on the left, this is most of the colored data points there are just the accumulation of stellar mass in galaxies. And the hollow red lines are from a compilation by Rhee et al. Of omega H1 measured in different ways. And what you see is from redshift 4 to 0, the mass in stars has grown by a factor of 30. And the mass in H1 has stayed almost exactly the same. So for that to be true, it says that basically the creation rate of H1 through cooling has to be equal to the destruction rate of H1. And that destruction rate is effectively going to be some combination of outflows and star formation. So the destruction rate of H1 is 1 plus eta times the star formation rate, where eta is this famous mass loading factor that we discussed at some length yesterday afternoon in Evan's nice session. What we'll see later in the talk is that at the relevant scale, the H1 disk and the stars, this mass loading factor is order unity for the stellar mass, for the L-star galaxies that really dominate the stellar mass budget. So this essentially implies that the creation rate of H1 is, sorry, I think I need to minimize. I've got my thumbnail covering my screen. Yeah, so it implies the creation rate of H1 has to be a lot less than the baryon accretion rate. And that suggests that when this 10% factor is not really being set by anything happening inside the galaxy, it's determined by the effectiveness of converting warm CGM baryons into cold ISM. So why do we expect feedback would couple exceptionally well to the circumgalactic medium? It's hard to couple feedback to the disk, right? If you have feedback in the disk gas has a high volume density, and that means it's will cool rapidly. It's hard to keep it hot. It has a high column density, which means when you push on it, it doesn't move very much. And it has a very unfavorable geometry. So if you release energy in the disk, it finds a path of least resistance and just blows out into the halo. In contrast, the circumgalactic medium has low volume densities, low column densities, and a sort of quasi-spherical geometry. So it's going to capture whatever energy or momentum is dumped into it. So I think these sorts of arguments really explain why I think the circumgalactic medium is really the battleground where accretion is fighting with feedback. So let's then talk a little bit about how hot winds are created by starbursts. So in round numbers, for every solar mass of stars formed, you get about 10 to the 49 ergs of kinetic energy from supernovae and from stellar winds. That's about 10 to the minus 5 c² in physics units. And that doesn't sound very impressive, but the potential well depth of a galaxy like the Milky Way is only roughly 10 to the minus 6 c². In this conventional picture that was first proposed by Chevalier and Clegg, these stellar ejecta are thermalized in shocks and produce hot gas. The temperature is of order 10 to the 8 Kelvin, modulo these factors alpha and beta. So alpha is the thermalization efficiency. If radiative losses are negligible, then alpha is 1. And beta, I'm going to call the poisoning factor to make it distinct from the mass loading factor. So beta is 1 for pure stellar ejecta. And as you mix stuff in, then beta can be larger than 1. Pressure of this gas is much greater than the surroundings. It's going to expand along the path of least resistance and blow out into the halo and form a sort of wide-angle bipolar wind. If you just have conservation of energy, you have adiabatic expansion of this hot gas, and the terminal velocity of the wind is going to be something like 3,000 kilometers per second with these alpha and beta factors. The kinetic energy flux carried by the wind is about 10 to the 42 times the star formation rate if radiative losses are negligible, and the momentum flux of the wind is about 5 times 10 to the 33 times the star formation rate, again for alpha and beta equals 1. And because this material in principle could be pure stellar ejecta, it could have a very high metallicity. So the metallicity in alpha elements produced by core collapse supernovae is 1 plus 5 over beta times solar. So here's 20 years of simulations. On the left is a simulation by Strickland and Stevens in 2000 showing a bipolar wind. And on the right is Evans' most recent work from last year. And yes, we've made progress. But I think conceptually, the picture proposed by Strickland and Stevens is still, I think, conceptually accurate. That is, we have most of the volume being occupied by this tenuous and energetic wind fluid. And what we actually observe in emission or absorption comes from denser material that is either interacting with or possibly was created from the wind fluid. And it has small volume filling factors. So now let's take a quick guided tour through the multi-phase wind in M82. So we see warm gas on the left in H alpha. We see hot gas, 10 to the 7 K gas in X-rays in the center panel. And on the right, we actually see dust scattering FUV light from the central starburst. And you can see the structures are remarkably similar in all 3 bands. The scale here, these inserts are about 20 kiloparsecs in height. Let's talk about the driver of the wind, this wind fluid. Do we actually observe it directly? And the answer is yes. We see it in M82 and in about a dozen other starbursts directly through the hydrogen and helium-like iron lines at 6.9 and 6.7 keV. These are signposts of extremely hot gas. In the case of M82, the temperature is about 60 million degrees. If you allowed this gas to not suffer any radiative losses and just expand adiabatically, it would reach a terminal velocity of about 2,000 kilometers per second. So it's detected as a sort of ghostly blue glow in the central region of the panel on the right, which is just color-coded by energy bands in the X-rays. It's only detected in the central region, and that's because adiabatic expansion and cooling causes the gas, this hot gas, to effectively disappear. It becomes very low in density and adiabatically cools. Now, what we commonly think of when we think of X-rays from the wind is not the wind fluid necessarily. It's gas that's roughly an order of magnitude cooler than what we see in the very center of the galaxy. So its temperature is something like 4 to 10 million degrees. And at least in the soft band below sort of a half a kilovolt, charge exchange becomes important and contributes about 20% of the total X-ray luminosity. And this is X-ray emission produced by an interaction between highly ionized and neutral gas. So you can see from the picture that gas at 10 to the 7 K is clumpy. It's not volume filling. There's structure. There are filaments and structures that actually correspond to some of the structures we see in the H alpha image. Right in the central starburst, the elemental abundances are supersolar, about 3 times solar in silicon and sulfur. But if you go further out into the outflow, the abundances are roughly solar. So in the outflow, this is not consistent with this gas being pure stellar ejecta. Probably the most familiar phase is what we see in H alpha emission. These are just a couple of pictures of the inner and outer H alpha filaments in M82. And you can see just from looking at this that this is very clumpy filamentary material accelerated by some kind of momentum transfer from the wind fluid. And it has a very small volume filling factor, something like 10 to the minus 3 to 10 to the minus 4, depending on the radius or the geometry that we assume. Now, one important point that I think doesn't get talked about enough is that it's possible to actually measure the momentum flux of the wind fluid. And that's possible because using optical data, we can directly measure the electron densities and electron temperatures, and we can actually measure the pressure in the flow as a function of radius. And in this plot on the left-hand side, the black solid dots are measurements of the pressure in the warm ionized gas in M82 as a function of radius. This is log R on the x-axis. So we're going from the central starburst out to a little beyond 1,000 parsecs. We can also measure the pressures using X-rays. This is a little bit tricky because we don't know the volume filling factor, and the pressure is going to depend on the inverse square root of the volume filling factor. So the minimum pressures these hollow dots are the X-ray pressures, and I've adjusted them assuming a volume filling factor of 20%, and that was done a bit as of a cheat to make the pressures in the X-rays sort of line up with the emission line gas. If the volume filling factor was 100%, these would be lower by a factor of about 2. But I think it's fairly obvious from the X-ray image that the volume filling factor of the hot gas can't be 100%. So the tiny little dots are basically just doing the stupidest possible thing, which is just take the standard Chevalier and Clegg model, scale to the star formation rate in M82 and the radius of the starburst in M82. And you can see that the model is in excellent agreement with the pressures that we measure. Now, in this model, in the central region interior to a few hundred parsecs, this is the thermal pressure because there is no wind there. It's just hot gas. The sonic point of the wind is about the starburst radius, and so at radii larger than a few hundred parsecs, ram pressure takes over, and you get this 1 over r squared pressure dependence in the model. And one of the things that's been puzzling me, I guess, is in this emerging popular picture in which the 10 to the 4 K gas is somehow cooling out of mixing layers associated with the hot gas, would you expect this gas to be at the same pressure as the ram pressure of the wind, rather than just the thermal pressure of the wind fluid, which is going to be considerably lower because the wind is supersonic? In any case, you can use this to measure the momentum flux in the wind. You have momentum per unit area. Momentum flux per unit area is the same thing as ram pressure. If you just multiply that by the surface area, you get the momentum flux. And in this case, the momentum flux in the wind fluid matches what we expect the input from the starburst. Now, what about the structure and kinematics of this warm gas? If you do a detailed study of the kinematics, this is Fabry-Perot data cube 3D mapping of the outflow by Shotwell and Bland-Hawthorne, what you see is that the kinematics and structure of the gas implies that the gas is flowing out along the surfaces of hollow bicones. So this is projected velocity as a function of distance from the starburst, and the lines are double peaked because you're seeing emission from the front side of the cone and the back side of the cone along each line of sight. You can also see that the gas rapidly accelerates. The radius of the starburst is about 300 parsecs, so this has reached its maximum velocity very quickly as it exits the starburst, and it reaches a maximum observed velocity of about 300 kilometers per second. In the modeling that they did, if you deep project this to get the true outflow speed, it would be about 600 kilometers per second. Now this is just overlaying the warm gas, which is shown in contours, with the hot gas, which is shown in X-rays. From looking at this, it's a little bit unclear what's going on, but let me go to the next slide. This is actually taking a ratio of H-alpha and soft X-rays. And in this picture, the orange and yellow regions are regions in which H-alpha is bright and the soft X-rays are relatively faint. And the green and dark blue regions are areas where the X-rays are bright relative to H-alpha. And what you see is, although it's quite messy, it really looks like the warm gas at 10 to the 4 K is sort of enclosing the X-ray gas. The X-ray gas is interior to or upstream of the warm gas. So there's clearly some kind of macroscopic interface between the hot and warm gas in the system. We also see a magnetized relativistic phase, which is traced by synchrotron emission from cosmic ray electrons in a magnetic field. This has been known for some time. This is the most recent paper I could find on the radio properties of M82. And what they find in this case is that the field geometry of the magnetic field is radial in the region of the outflow. Assuming equipartition, the magnetic pressure, B squared over 8 pi, is about 10% of the thermal pressure in the wind. And in this paper, the authors basically are interpreting this as the magnetic field is being advected by the wind fluid and carried out with the field lines getting stretched in a radial direction. Just to complete the picture, there's also molecular and atomic phase. This is sort of a cartoon put together by Leroy et al., in which the cooler material, the molecular and atomic phases, are in a sort of fountain flow, roughly 100 kilometers per second, that surrounds the region of hot and warm gas. Okay, so now what I want to do is basically try to convince you that M82 is not some weird atypical object. It's atypical of galaxies today, but it's typical of starburst today. And this is a cartoon put together in a paper that Dave Strickland led some time ago. And it's just a schematic, which I think is a cartoon representation of what I was saying before with M82, that we have a sort of central cavity filled by this wind fluid, which is not emitting very much. And then we have these sort of limb-brightened structures that are visible in H-alpha and soft X-rays around the boundaries of this cavity. So I'm going to just show you some examples. This is NGC 3079 in the central region. This is a kiloparsec scale bubble. You can see these filaments, kind of a filamentary bubble structure zoomed in on the picture on the left-hand side. And the red is the H-alpha from HST, and the purple are the soft X-rays. If you measure the kinematics of the gas, put a slit along this, you see the same thing you see in M82, that there are split lines from emission from the front and back of the bubble with implied velocities of order 600 kilometers per second. This is going into the outer part of NGC 3079. These are H-alpha filaments extending out about 10 kiloparsecs on the left-hand side. And then on the right-hand side is from the recent paper by Hodges-Gluck et al., showing the soft X-rays and probably dust-scattered FUV emission on scales of tens of kiloparsecs. And again, these are all sort of this limb-brightened filamentary structures. This is the core region, kiloparsec scale region of NGC 253. In soft X-rays on the left-hand side, you see again this limb brightened structure to the lower left of the nucleus. And then on the right-hand side, this is just an azimuthal cut of the surface brightness in H-alpha and X-rays, showing limb brightening in both H-alpha and X-rays. This is the outer halo of NGC 253 on scales of tens of kiloparsecs. Again, soft X-rays on the left-hand side and H-alpha on the right. Here's scaling up by a factor of 30 in star formation to Euler's merger ARP 220. Again, soft X-rays on the left, H-alpha on the right, these sort of limb brightened double bubble structures. Same thing in the Euler NGC 6240, filamentary structures in H-alpha and X-rays that align with one another. And then most spectacularly is a recent paper by Rupke et al. This is something that's probably a factor of 3 to 10, even more powerful than ARP 220. It's a redshift of about a half. And this shows ionized limb brightened bubbles stretching out roughly 50 kiloparsecs in radius from the central starburst. Okay, so I want to just shift gears while I'm talking about measuring spatially resolved structure, because one of the other ways of doing it, so far we've been talking about emission, nebular emission from warm or hot gas. You can also use resonance scattering and associated fluorescent emission to study winds. This is just showing a picture on the right-hand side. This is the ground state and fine structure levels in silicon-2. If a photon is absorbed from the ground state, it can go to one of the excited states, and then it can either decay back to the ground state, which is resonance scattering, or it can decay to the fine structure level, and this is called fluorescence. So as for every photon that's absorbed in the outflow, that photon is going to be re-emitted either as a resonance line or an associated fluorescent line. And what you can immediately grasp is that the relative strength of the absorption lines and the emission lines are going to depend on the relative size of the outflow compared to the aperture of the spectrograph used to measure the spectrum. If the outflow is large compared to the aperture size, as is shown in the left-hand side there, then you get all the absorption because you see the full starburst. So the absorption line is strong, but most of the emission is outside your aperture. And so you get a strong absorption line with a weak emission line. And that means, in principle, one can learn something about the size and structure of outflows by comparing the absorption lines and the emission lines. This is just some examples. This is an ongoing project with my graduate student, Binji Wang. We are using COS UV spectra of Lyman break analog galaxies. These are low redshift starbursts that were chosen to have properties similar to Lyman break galaxies. And here the the data for this galaxy are in orange. This is silicon-2 1260. It has an associated fluorescent line at 1264.7. And the data are shown in orange. If you have a starburst wind and you have an aperture large enough to capture the entire wind region, you would get a spectrum like what's shown in black. So a very strong fluorescent emission line. You can see the data, the fluorescent line is much weaker. And so we're trying to make models to sort of use these to infer what kind of structure the wind would have to be consistent with the weakness of these fluorescent emission lines. And what we're finding is that you cannot fit the spectra of these galaxies using a sort of fiducial density law of like R to the -2. That's too centrally peaked, too much emission ends up in the aperture. You have to have a radial density profile that's considerably shallower than that. And that has very interesting implications for the structure of the wind. Even better is the case where you can spatially resolve the resonance emission. And this is from a recent paper by Burchett et al., where they've used KCWI to map magnesium-2 wind emission from a star-forming galaxy at a redshift of 0.7. They detect magnesium-2 in emission out to radii of about 20 kiloparsecs. And again, in the modeling, they find that they have to have a velocity which is falling with radius and a density profile that's considerably shallower than R to the -2. So this is consistent with what we're inferring from these analysis of the cost spectra. Okay, so now I want to switch gears and talk a bit about the systematic properties of galaxies. What are the important parameters that can be derived from the data, and what are some of the assumptions that we have to make? This is something that Evan covered very nicely in her talk yesterday, so I hope many of you probably heard it, so I can go through the introduction to this relatively quickly. I'm going to primarily focus on the large data sets, which are only really available for these sort of down the barrel absorption lines. But I wanted to start out not using absorption lines, but going back and talking about this business of measuring radial pressure profiles that I showed you in M82. So we can do this in more than M82. M82, we have the best data, but we can actually go through the same exercise and try to estimate the radial pressure profiles and use those to infer a momentum flux. So we're just basically measuring the momentum flux per unit area as being the pressure, and then integrating over the area, we can get the momentum flux. And what's shown here is the momentum flux we estimate using this technique on the y-axis versus the injected momentum flux from a starburst on the x-axis. So you can see that the line through the middle is just the one-to-one line. So the measured momentum flux in this hot wind fluid is comparable to the amount of momentum injected by the starburst. Okay, so now I'm going to focus on absorption lines. And there have been quite a few studies, John Chisholm, Rangman Bordoloi, among many others, Crystal Martin. People have used this technique to try to infer properties of outflows. There are many papers on this subject. I'm going to focus on a particular sample that I worked on with Sanch Borthakar, and mainly because I'm the most familiar with the assumptions that I made, but also I think this is a very nice sample in the sense that most of these are Lyman break analogs. So what we learn from studying these, I think, is relevant to galaxies at higher redshift. We restricted the sample to only cases where the aperture covered the entire starburst. So we're talking about global properties. And the goal of this was to kind of figure out what these scaling relations look like and confront the models and simulations with them. This is just showing profiles of the kind that we work with here. This is showing 5 different ions. You see a range in velocities with pile up with strong absorption near V equals 0, and then the absorption becoming weaker as we go to higher velocities. Okay, so how do we do this? There are a number of problems that let me briefly walk you through. One problem is that how do we define the velocity, right? We want to measure an outflow rate, and to measure an outflow rate, we need to have a velocity. You can see that there is no well-defined velocity here. Sometimes people select a maximum velocity, which in this case would be sort of 800 or 900 kilometers per second. That's kind of a ill-defined quantity in some cases. In the paper that I'm going to summarize the results, we actually use the centroid. So it's sort of a non-parametric measure of just the centroid of the line. That has some problems as well, but it's the most straightforward thing to do. We also need to know the column density. And the problem with getting the column density is that these lines are often optically thick. So the strong lines that are easiest to measure have significant opacity, and that means that the basically equivalent width of the line is relatively insensitive to column density. So what we did in this paper was to actually use weak lines, which are unsaturated, and measure the column densities in those lines, and then make the assumption that these are measuring lines from typically things like sulfur 3 and sulfur 4, magnesium or iron 2, and then basically we spanned a large enough range in ionization state that we could do a rough ionization correction, and we then converted these columns in metals into hydrogen or total columns, assuming that the metallicity in the outflowing gas was similar to what was derived from nebular emission lines for the starburst itself. So what are the results of this exercise? we find fairly strong correlations between the velocity of the outflow and both the stellar mass or circular velocity that's shown in the plot on the left-hand side and with the star formation rate shown on the right-hand side. This is not surprising. Many people have found qualitatively similar results. We thought it was maybe more physically instructive to look at a sort of normalized outflow velocity. In other words, the velocity normalized to the rotation speed of the galaxy. That's what's plotted on the left-hand axis here. And we wanted to also have then something that was a more normalized star formation rate on the x-axis. So this is star formation rate per unit area. And what you see is a steep rise in velocity. This normalized velocity is a function of star formation rate per unit area, and then it sort of saturates once you get above a star formation rate per unit area of about 100 solar masses per year, per kiloparsec. The scale of these outflows, what's plotted here is this Vmax, the maximum velocity, and the velocity in these strong outflows on the upper right-hand side of this plot are typically 5 to 10 times the circular velocity. If you use the centroid velocity instead, they're still about 3 to 5 times the circular velocity. So for these strong outflows, the velocities that we observe in the warm gas are significantly larger than the escape velocity. Okay, I see I had my slides out of order. This is basically a slide that explains what I walked you through before. We take a centroid velocity, we take weak unsaturated lines, and then finally there's this question of what you assume about the radius. So to get outflow rates, you have to adopt a value for the radius. The radius is something that's poorly constrained. Basically, we just adopted a scaling where the radius is assumed to be some dimensionless quantity beta times the radius of the starburst, and beta we chose to be of order 1. Okay, so doing that, we can now measure the outflow rate as compared to the star formation rate, and this is a plot that Evan showed yesterday. And within the uncertainties, basically the answer is the star formation rate is of order, the mass outflow rate is of order the star formation rate. We can also measure the momentum flux. We have a mass flux, you multiply that by V, you get a momentum flux. And what we find is there are basically 2 regimes. There are these data points at the upper right where the momentum flux in the warm gas, now this is different from what I started out. In the beginning, I was talking about the momentum flux in the wind fluid. This is the momentum flux in the 10 to the 4 K gas. And there are a family of these objects in which the momentum flux in the warm gas is comparable to the injected momentum flux from the starburst. So there's been a very effective coupling of momentum from a hot wind into the warm gas. On the other hand, there are these data points in the lower left part of the dot plot where only about 10% of the momentum available to the gas has been transferred to it. So the momentum flux transfer has been ineffective in these so-called weak winds. So what do we think is the physics going on? I think the simplest model or way of thinking about this, I think, is just to try to gauge the relative importance of the outward force acting on this material due to the momentum flux in the wind and the force of gravity in the inward direction. And it's possible if you do this, this is almost like an Eddington limit kind of argument or similar to it. You can define a critical momentum flux from the starburst in which the momentum flux from at the location of this cloud will produce a force on it that exceeds the inward force of gravity. And this critical momentum is written down below the figure there. Beta is this sort of fiducial radius of the starburst, the column density, the mean mass per particle, and the circular velocity squared of the galaxy. We know all of these things except for beta, and if we just take beta to be roughly of order unity, we can make the plot above where we compare the momentum flux delivered by the starburst on the y-axis to the critical momentum flux needed to overcome gravity on the x-axis. And what you can see is in the majority of our sample, the momentum flux from the starburst is roughly an order of magnitude larger than what's required to overcome gravity. So it's not surprising that we see an outflow. And in fact, in these strong starbursts, the ratio of momentum available compared to the amount of momentum needed to overcome gravity is, much larger than 1. And in fact, there's a good correspondence in these two plots. The cases where there's been an effective transfer of momentum from the wind fluid to the gas, points in the upper right, are the same objects in which the momentum flux from the starburst is much larger than what's needed to overcome gravity. Now, in this picture, there's a very natural explanation then for why winds evolved with cosmic time, why they're not so important now and were very important in early times. And that's because you can rewrite this ratio of outward to inward forces as being proportional to the star formation rate divided by RV squared. At fixed mass, the star formation rate goes like 1 plus z to the 2.5. That's a specific star formation rate. In other words, is evolving like 1 plus z to the 2.5. And effectively, by definition, at fixed mass, RV squared is independent of redshift because RV squared is just mass. So this means that as you go from redshift 0, you're in this regime where there are no winds or only very weak winds. As you go to higher redshift, because of this 1 plus z to the 2.5, this ratio in typical star-forming galaxies grows. And by the time you're at a redshift larger than 1, you're in this regime of strong winds. Okay, so I want to spend the last 10 minutes talking about how winds might impact the circumgalactic medium. And I'm going to start at redshift 1 because that's where we have the most data. And it's in this regime, as I mentioned on the previous slide, where you don't have to look at starburst to see winds. Typical galaxies on the star-forming main sequence are driving outflows. In the left panel, these two plots are taken from a recent paper by Lan and Mo. These are based on stacking sight lines of quasars associated with either luminous red galaxies in the Sloan survey or emission line galaxies that were used in the EBOS survey from Sloan. So it's a very large sample with lots of stacks available, and this enables you to reach equivalent width limits of a few hundredths of an angstrom in these stacks. And there are 2 points to take away from this. One is that in the inner CGM, interior to about an impact parameter of 100 kiloparsecs, there's an excess of magnesium-2 absorption in the emission line galaxies compared to the luminous red galaxies. This is comparing things with in kiloparsecs. This would be even more impressive if you rescaled the x-axis on the left-hand side to be in units of the virial radius, because the red galaxies are quite a bit more massive than the blue galaxies. On the right-hand side is showing for iron-2 and magnesium-2 in the stacks, the fact that the magnesium-2 lines within this region interior to about 100 kiloparsecs are stronger along the minor axis than along the major axis. Now, this is a very nice paper that I think is pretty much consistent and goes further than the Lan and Mo paper in terms of what they're able to model. This is from Schroeder et al. Based on Muse data, redshift about 1.1 to 1.5. On the left-hand side, what they find is a bimodal distribution of magnesium-2 absorption. There's a peak near 0 that would be in the plane of the galaxy. And then there's another peak roughly from 50 to 90 degrees, which would be along the minor axis. The interpretation of this is that the peak close within, sort of 10 degrees of the major axis represents accretion in the plane of the disk. And the peak, the broad peak from 50 to 90 degrees would represent an outflow. What they're able to do is, with a model of the outflow, sort of biconical flow, is to try to make some inferences about velocities and mass loading factors. The middle panel shows the velocity in units of the escape velocity on the y-axis, and then the stellar mass of the galaxy on the x-axis. And you can see that it's only when you get down to below about a few times 10 to the 9 solar masses that the inferred velocities from these models will exceed the escape velocity. These are on scales of roughly 100 kiloparsecs. On the right-hand side is the estimate of the mass loading factor, and you can see there's a lot of scatter. The data points are shown, and then the colored lines are various theoretical model predictions. On scales of 100 kiloparsecs, the mass loading factors are measured to be of order a few. There's a wide range, as you can see. By eye, the median looks like maybe 2 or 3, and it seems to decline slowly with radius. Or sorry, with mass, I'm sorry. What about redshift 2 to 3? This is when every star-forming galaxy effectively is driving a strong wind. This is some seminal work by Chuck from 2010. These are stacking galaxies behind the circumgalactic medium of foreground Lyman break galaxies. The actual stacked spectra are shown on the left-hand side, and the right-hand side is basically showing the strength of the absorption lines, equivalent width of various ions as a function of impact parameter. And what you can see is that you detect not only Lyman alpha and Lyman beta, but you detect heavy elements out to a radius of about 100 kiloparsecs, and then it looks like there's some sort of cutoff beyond 100 kiloparsecs where the lines get rapidly weaker. And Chuck can talk about this, of course, soon, but I think the interpretation of this is sort of representing the zone of influence of the wind. This region interior to about 100 kiloparsecs is where these heavy elements are flowing out into the circumgalactic medium. At redshift 0, the data are quite limited, and that's because at redshift 0, only relatively rare galaxies drive winds. And if you look at COS halos or COS gas, they're not very large surveys to begin with, and they're not large enough to really include starburst galaxies. So we had to actually do data mining. We took 1 million galaxies in Sloan. From them, we selected 17 starburst galaxies that had a quasar that was bright enough within an impact parameter of about 200 kiloparsecs to observe with HST. The parameters for the starburst were derived from the SDSS spectra. These are M82-like starburst, something like 10 to the 59 ergs in total energy, injected over a few 100 million years. Roughly 20% of the mass of the galaxy has been formed in this burst, and this is all described in a paper by myself and others a few years ago. Well, what did we see? We're using COS burst and we're using COS gas and COS halos as our control sample and selecting star-forming galaxies. And those are shown in blue in these two plots. So this is the equivalent width of silicon-3 on the left-hand side, and carbon-4 on the right-hand side, as a function of normalized impact parameters. So this is impact parameter in units of the virial radius. And what you can see is that the starbursts in red have significantly stronger metal lines on large scales. So we're going all the way out to the virial radius. You see an enhancement by a factor of several to 10 in the strength of these metal absorption lines, with a covering fraction of about 50% in the outer CGM. We also see evidence for supervirial velocities. So on the left-hand side are the widths of the lines in the control sample. In the bottom panel there, typical velocities are, the lines are maybe 100, 150 kilometers per second wide. In the COS burst sample, there are many much broader lines, and on the right-hand side is just a stacking the Lyman alpha absorption lines in the COS burst sample, and that's shown in black. And what's shown in red is what you would expect if these were just clouds orbiting in the gravitational potential of the halo. So there's evidence that not only are the lines stronger in the halos of starbursts, but they are kinematically distinct, showing evidence that something other than gravity is involved in their motions. Now, can this really work? We just did an incredibly simple-minded model. We just took the classic windblown bubble dating back to Weaver et al. In 1977 and retooled it to the circumgalactic medium. So this is just something that can either be driven by energy or by momentum. we took our mean starburst age of 300 million years. The mean energy injection rate is 10 to the 43 ergs per second. And then we use similarity solutions from Dyson 1989, assuming that there's a sort of volume filling X-ray halo whose properties are given a total mass of about 10 to the 10 solar masses with a density that drops like 1 over R. This is sort of loosely based on the Milky Way's halo. And what you find is that the outer radius of this wind-blown bubble is roughly 200 kiloparsecs in the case of an energy-driven bubble. And even if you have radiative losses in the wind fluid and it's driven by momentum, you still get out to nearly the same scale. So it is plausible that the starburst could be affecting the circumgalactic medium all the way up to the real radius in these systems. Well, on my next to last slide, I wanted to advertise something that I think is very exciting in terms of the future prospects for learning about the interaction between outflows and the circumgalactic medium. The Subaru Prime Focus Spectrograph project is going to deploy roughly 2,400 fibers over 1.25 square degree field of view at the prime focus of the Subaru telescope. We will have spectra with resolution of about 3,000, covering 3,800 angstroms to 1.26 microns. We have 360 nights for the survey over 6 years, starting 2 years from now. And we're going to be doing many, many things with this, but one of the things that's the most relevant to this talk is that we can use combinations of quasars and background galaxies. We estimate that we'll be able to probe about 60,000 sight lines through the circumgalactic medium of galaxies with impact parameters less than 200 kiloparsecs over a redshift range of 0.6 to 2.4. And by stacking these stacks of 100, so we will be able to reach limiting equivalent widths of a few tenths of an angstrom. So I think we'll be able to really expand on the kind of work that I showed you with the LAN and MO approach, but now over a wide redshift range with more ions and a greater diversity of galaxies. Okay, so let me just leave my conclusions here. You can read them, and I'm happy to take questions, or I guess we're going to take our little coffee break and then come back for the panel discussion.
Excellent. Thank you very much, Tim. That was great. Good overview, and a lot of points for discussion later. Yeah, so it's 9 o'clock now, Pacific. We will reconvene in 5 minutes, 10 minutes? We'll say 5 minutes. We'll reconvene at 9:05. So go ahead and get some coffee or do whatever you need to do. And I encourage people to look at the Slack channel, week 5 outflows, Halo 21 week 5 outflows, for some of the points that have been made by members of the community. Respond to them, upvote them, add your own comments and discussion points, and I will be selecting those. And I encourage that to be the point where you mark things as opposed to just raising your hand or blurting out in the discussion. So we'll reconvene in 5 minutes.